Hello, 6 o'clock. Let's get started. Let me start the recording as well. Okay, so, I see there are a couple of interesting questions on the discussion side. So let me first share it with you. Share. Okay, so Joshua has a question about this how the double words are stored and fetched from the memory. So all double word is also kind of a multi-byte words, right? Multi-byte data. So as the other multi-byte information, this is also stored in a similar way. So it will store like a 8 byte in the memory. Uh, so one fetch from the memory gives you like 32 bit, which is a word. So double word would need uh, like two read from the memory. So memory would be read twice in that case to retrieve a double word. So there is one catch there though. Like if you think that is inefficient somewhat, like for a double word usage, it is not actually. What happens in reality, um, this memory on board, that DRAM and all this stuff, are not fetched address by address. They are fetched in a group, in a batch. Okay, so like a chunk of data are pulled out on the from the main memory into the computer processor, and then they are processed inside the. Probably you have heard the term cache memory, um, but let's not go deep into detail of that cache memory. That's more like a part of CS47 or computer architecture study. Um, but we'll see there in that course like how that things works. But for you time being, just assume these double word datas or single word datas from the DRAM, the memory on board, are not fetched single one data at a time. It's basically a batch mode loading of chunk of data together, and they are stored temporarily inside the processor in a part which we don't know yet, we haven't studied yet in this class, but it is there. And now they are being processed like a double word, single word, byte, etc., as you want to do. Is that okay, Joshua?
Yeah, that answers my question.
Okay, great. So next one from Carter and also from Charlotte is kind of related. They are related actually. I know those specific topics, especially the alignment explanation, can be like confusing to you. So let me try to actually re-explain those part. Okay, once more, and hopefully that explanation will cover this question. If not, or if there are other questions also, please let me know. Okay, so at that point, let me just share the Jamboard to start explaining that part.
Professor, actually, I have a question
Yeah,
about the. I don't get it. Why we drop 2 bits from MIPS to the memory?
yeah, these are all related. Just hold on to my explanation, okay? Just I'm trying to do the explanation. So, okay, share, what is that? Yes, okay. All right. So, as we so far we have discussed this byte addressable memory from the processor perspective. That processor thinks that each addresses contains like like 1 byte. Right. So here is your microprocessor. microprocessor, to its world, your memory is byte addressable. So that means like it's basically like it sends like 32-bit as an address. In this world of view, your memory, each address is containing a byte, like 8-bit, 1, 2, 3, 4, 5, 6, 7, 8, 8-bit, each address. And there are 0 to 2 to the power 32 minus 1 addresses, right? Which gives in total 4 gigabyte of memory storage. Now, this is the microprocessor's view of the memory. In reality, your memory as a device, if you look on the board, it's a word addressable device. It's a word addressable device. Okay, so that means each of these container contain 32 bits, right? Each of these container 32 bit, or like in a byte term, each of these contain 4 byte. Like byte 0, let's say byte 1, byte 2, byte 3. Right, and so on and so forth. So all of these has, each of them contain 4 byte each. So if it has to be a 4 gigabyte of memory, right, your size is 4 gigabyte, your size is 4 gigabyte, and each storage at each address, okay, each address contains like 4 byte. That implies number of addresses. Number of addresses is of course like then 4 multiplied by 2 to the power 30 byte divided by 4 byte equal to 2 to the power 30. So there are a number of addresses available to the power 30. So it is addresses are basically from 0, or let's write in the opposite way. Like let's start from 0 here at the bottom, and let's say here at the top, to the power 30 minus 1. So you see like, let me write the same way here as well for this guy. The conceptual memory that processor thinks it's accessing is 2 to the power 32 minus 1 from 0. But from, for the memory, it is really there are like 2 to the power 30 addresses for a 4 gigabyte of memory, because each address for the memory real physical device contains 4 byte each. So, so what happens? So basically, on board, we have a connection of 30 bits on the address, right? Okay. So how this, now the question becomes like, processor as a physical device is actually sending 32-bit address, and physical device of the memory on board is connected with the 30. What happens to the 2 bit? 2 bits get dropped. Means on the physical line, like these are 32-bit line, which is like, let's say, let's mark it as address from the memory. address from the processor, and let's mark this guy, it's address towards the memory, right? So what happens is basically this address towards the memory (29 to 0), that bit, like this is 30 bit. Let me just fix my handwriting there. Okay, 29 to 0 is equal to address issued from the processor um, 9 dropped, okay, 31 till 2, 31 to 2. So the LSB side, 2 bits are dropped from the whatever address is coming out of the processor. 2 bits are dropped LSB side, and higher 30 bits from 2 to 31 is being placed to address going into the memory as bit 0 to 29. Okay, so that means address is somewhat transformed, and you see, like, for that means, like, with this relation, what we can conclude is that per 4 address, one common address is sent to the memory. Means what? Imagine your address is address from the processor. Address from the processor is let's say 0, 1 point of time, 1, 2, 3. Let's pick up 4 as well. 4 hex 0, 1, 2, 3, 4. Then what is the, according to this relation, this one, what would be my addresses going into the memory? So remember, like, initial 2 bits are dropped. So this guy is like a 0, 0, 0, all 0, last is 0, 0. This guy is bitwise. If you expand to the 32 bit, it becomes 0, 1. This guy is 0, 0, something like 0, so 1, 0. This guy is 1, 1. And this guy is 1, 0, 0, right? So what happened to the other address then? If we drop, like, initial 2 bits, this is practically 0, right? We drop the 2 bit, drop the 2 bit, drop the LSB 2 bit, drop LSB 2 bit, drop LSB 2 bit. So this is 0, this is 0, this is 0, this is 0, this is 1, right? So that's what I mean, like from, like, for each set of 4 addresses from the microprocessor, one unique address goes into the memory. Is that clear so far? Like, any question? Okay. So now, as we understand this part, so that means memory as a device, it will always send me back a word, right? And it's the same data. Let's say my processor is trying to read from 0, 1, 2, 3. So for each of these addresses, same data will be coming, right? Same data will be actually read from the memory, right? And remember, like, For a load word, you remember our alignment like rule, like among these four addresses, right, only load word can be applied here for this guy, because this is the one which actually I should actually mark it on another way, which basically here, this is load word compatible, right? And this one is also load word compatible. For the half word, you can either use this load half word or this, the even number. And for all these three, you can use the load byte. Now all these four, like load byte is possible for this address. So load like byte can be done from any of these addresses, and in fact this address too. And half word is also can be done at this address from address perspective. But whether what we are doing like a load word or a half word or a byte, it doesn't matter from the memory device perspective. It will still return you back the complete 32-bit, the complete word from it. Now, inside the processing, when in processor gets the data, it actually knows that what it's trying to do, whether it is trying to do a load word or a load half word or a load byte from what address, whether load byte from the 2 or 1, etc. Right? So if it is a let's say it is a load byte on the address 0, right? That means we are going to pick up this, right? So what it will do, it will basically go and take, let's say 32-bit wise, let's say it sends out some data like this: A, B, C, D, that is 16-bit, 1, 2, 3, 4. Okay. So for a byte, load byte, it will pick up this. Okay. Load byte unsigned. If it is load byte signed, then it will basically sign extend this 8-bit into 32-bit and load it. And load byte unsigned, it will pick up this bit and prepend with 0. That is 0 extension will happen there. Now, if it is a half word from the address 0, okay, so what it will do, it will basically pick up this half word, L, B, H, Q. Sorry, there is nothing called L, B, H, Q. Load half word unsigned. And if it is a full word, then, well, we all know, like full word is this, the whole thing is my full word. Now let's see if it is going to do a half word from 2, right? 0, 1, 2. So we are talking about this thing, B2, B3. And this half word is basically this one, B0, B1. So for this half word loading from address 2, what processor will pick up from out of these 32-bit, the higher 16-bit. Okay. And what about the byte? Basically, let's say it is, let's pick up like this byte, like address from this address, this byte, which is like this, B2. So processor will pick up 1, 2, this one. This is load byte unsigned from an address 02. Oh, sorry, 03. So at the processor side, things get picked up. But from memory side, the complete word is sent back to the system. Question. Carter, is that answered your question?
So essentially on the processor side, it's the only place where it can see the individual bytes and such.
Exactly, exactly.
And it differentiates those single bytes. How again? I kind of got lost there.
So basically, it's, let's say, okay. So let's say you are having these the executing this instruction in the program, right? LBU from a memory 03. This is an address, okay? So this address get translated to a memory address of 0 by dropping the first 2 bits, okay? That 0 entire row is accessed, and let's say there is 32 bit of data, A, B, C, D, 1, 2, 3, 4. And now, what is this address 3 means? The address 3 from this complex word means we are trying to pick up this guy, right? In fact, like if you want to map it, like this part, okay, maybe I can read here. This is your address 00 from the address from the processor point of view. This is your address 1. This part is address 2. And this part is address 3. Right? So 0, 1, 2, 3. So that means this thing, LBU, load byte from the address 3, practically we're trying to picking up this byte, right? So far, so good, Carter?
Yeah.
Now, the memory sends back you the whole 32 bit. And out of that, which one is B3, byte 3, the highest byte is this one. So processor knows that, okay, if it is an address, if it is the address's last 2 bit is 3, right, 1 1, I'll pick up from this position. So processor knows exactly like what address it produced to access, and it knows it will get a 32 bit of data. Then it kind of breaks down the data and picks up the right byte intended for that address. So it picks up this guy. And your load SBU, let's maybe it is on the T0. So T0 will have AB value right there. It will extend that AB into 32 bit with a 0 extension and store it back into the T0 register. Carter, makes sense?
Yeah, that's very clear now. Thank you.
Charlotte, is there other questions? Yeah, except for number 3, I'll explain that. Related to this one. Charlotte?
Yeah, so how did, again, like since the address gets shifted right by 2 bits, how would you access the like very highest bits then? Because the very highest address values, since, oh, I guess it's only up to 2 to the 30th since the rest isn't accessible by the processor.
Right. Processor always has these, all the addresses accessible in the sense, see this even from the memory perspective, it is 2 to the power 30s, right? Each of these byte is an corresponds to individual address location from the processor perspective. That's how you're not losing any address space or anything.
Oh, okay, that makes sense.
Okay, so
Professor?
yes.
Can you go over the storing convention again? So like you wouldn't store a half word at B3, you know, it would have to be at B2. But the same convention follows for like full words. You have to start them at the very beginning of the memory of the address.
Right, right. So you are looking for the reason why that those rules, right?
Just wanted to confirm that you're only sending one row at a time on the memory side.
Right, exactly, exactly. So what is happening here, like uh, let's say I want to, in a system, I want to allow your access of load word from any address. Let's say I want to allow here. Okay, so that means what? Like we are starting from here. So this byte, so word from this point would be like this, 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 and this, right? So that means you see there are like, we need to read two rows, get two rows and combine the bytes into that to make it happen. A load word happen from an odd address like 1. And it's true for address 2, true for address 3. So that's why we are not encouraging anyone to use that. We are kind of disabled that way of combining things to make things simple and efficient. So that's the reason that why load word has to be in a boundary of like address divisible by 4 only. See, like 1 from 0 to 4 we are going, we are practically starting reading from these guys, right? So in that case, what will happen is that, so let's say we are reading from 4, then we'll basically start reading here, this byte, 1 byte, 2 byte, 3 byte, 4 byte. This is a complete one single row in the memory device, and we can read it in one shot. And that's why it is load word is always by 4. Now, how about the half word? So half word is basically either, let's say I want to give an access on any address, right? Let's say I want to access it from here. It's just now is the same problem. So I have to access this byte and a higher byte, right? Higher byte. So this storage and these bytes, that means I need to make a to read. Like if it is crossing the whole address boundaries, we are preventing that. Then the question becomes, why don't we just access from an odd address? We can, it's still 1, right? It is to avoid the electronic circuitry complexity. Just if we just let user or programmer to use only the even addresses, our circuit inside is a little bit simpler. That's the reason. And byte I can access from anywhere without any additional complexity. Make sense?
Yes, thank you.
Okay. Any other question before I move on to Charlotte's number 3? That question that is interesting.
So no matter what type of load you do, whether it's byte, word, or half word, it always does the full word space, always sends that always back.
Exactly. From the memory side, entire full word is sent. It's only at the processor side that data may be broken down into pieces depending on whether you are instructing a load byte or load half word or load word, that kind of instruction. It depends on the instruction, how it uh, breaks and then put them together. It's done at the processor side.
Okay. So then I assume the advantage of doing that is you can temporarily cache the other data in case you're about to use it, kind of thing.
Yeah, that would be one. That would be one. But I think, as I understand this industry, it's to start support these legacy systems. Like we started like in the 80s and 70s, we started with the very smaller memories, and bytes was kind of an good data, good amount of 8-bit is good amount of information that time, 16-bit then it comes. So we started to support this lower bytes, sorry, lower amount of information, lower, I'd say what is it, lower granular level of information like byte, half word, etc. like that. So we wanted to support that throughout, even now, right? Even now, with an advantage that hey, my character is a 8-byte data, right? It's an 255 ASCII code, and so on and so forth. So there are some utility to use the lower granular level data types, whereas from the memory operation perspective, these memories are going more efficient with this 32-bit at a time, and it can retrieve that. And definitely that point comes in, like we can actually store back those data into the processor, temporary memory storage like the cache, etc. So we keep on supporting them with this alignment restriction. That's the whole history of it. All right, there is no other question then. Let's move to the next question that Charlotte has, that what is this extern? What is this extern? Okay, so extern is directives so extern format is it extern some label name, let's say I name it a var underscore a, it can be anything, and then amount of storage. So I can here I can like 16, which means like it is a 16 byte. Okay, now there is some specific characteristics of this storage. Okay, specific characteristics of this storage. First of all, this address, so this extern will create an entry in the symbol table let's say we all know the symbol table contains a label name and address. It will create a symbol table entry, mark it as a global. First of all, this is a global label, and it will place an address. It will assign an address to this label, some address, let's say A. Okay, this A is in the range of so it will actually place them in this section of the memory. Now, what is so special about this? Remember in our global pointer memory study, like one lecture back with the MIPS, global pointer sits actually points just in middle of this address range. Okay, global pointer middle of this address range, so that with respect to the global pointer, using this as a base pointer, either you do a negative offset or a positive offset. Okay, you can actually access this entire address range. So all our extern are placed in this special data segment, okay, so that we can easily access using the global pointer register and also mark it as a global. One more distinction is that we do not need to initialize this space at all. No initialization. Whereas other way is that you can make a label like dot data, let's say VB dot word followed by 1, 2, 3, 4, A, B, C, D, etc. Then VC dot byte, you can put some bytes there, 1, 2, 3, 4, 5, 6, etc. So this will give you, make a symbol table entry, VB, VC, etc. in the data section, right? In the data section, which is for the MIPS. It is coming from, at least in the Mars. What is the data section start? I think 1001. So all this part, it starts from 1001,000, something like that. Please check this address. So it goes into that section of data. Yeah, it's after that, after this point, after this address. They start from this address. Okay, so maybe address B and C are placed, but we can still make it global by declaring like dot global VB, which is make this, mark this label as global. So there are extern is another way of defining global space to be referred by any program or program segment, which also goes in a very special section, which can be directly accessed by global pointer using global pointer as a base register. Charlotte, is that good? Or you have any other question like for this?
Yeah. I suppose for the data starting from like after global pointers range for up to like those FFFF,
Right.
those addresses, I guess, how would you access them?
So those addresses are accessed by it's basically, like what happens if you do something like load word, let's say $T0, and let's say you do a VB, right? So first of all, this is a pseudo word, pseudo code, pseudo instruction. So if you check, this pseudo instruction is broken down in the by the assembler like this. Assume this B is let's say 10010002, for example, right? For some reason. So what this assembler will do, it will do a Louis on $80 with 01001, or I $80, $80, 02, and then do a load word $T0, $80. So it will basically use the assembler temporary register to load that address and use an offset of 0 and use that AT register to load the word.
Okay.
Professor, can you solve the practice quiz at the end of the lecture 9?
End of the lecture 9. Okay, I'll try. Yeah, definitely. If not today, maybe next day. We'll see.
Okay, thank you.
All right, almost like 6:40, 40 minutes over. Let's take 5-minute break. 6:45-ish, we'll be back. Okay, let's get back. Pop quiz time. Can you please go into your canvas and see there is a pop quiz 3, and I'm just sharing. Okay, let me see the poll whenever you are ready. Okay, quiz password. Okay, whenever you are ready to enter the quiz password, please vote yes. Then I will distribute the password.
I didn't get the password.
No, I will share in another.
Oh, okay.
Yeah. So far 36 are ready, 37 out of 39, 37. 2 more people to go to find out the quiz, ready for the getting the password. 38 said yes, 1 more. Okay, I don't know who is not ready, but let me just share the password poll. Okay, which one? Okay, there it go.
I'm sorry, I cannot use the passcode.
It's in the poll.
Yeah, but I enter it, but it doesn't accept.
Oh, is that the case for anyone else? Or
It works for me.
okay, can you try reloading that quiz? Sometimes Canvas is like caching and stuff like that.
Okay, got it. It still doesn't let me in. Hello?
Is your caps lock on from inputting the Zoom password?
Oh, yeah, I'm sorry. Got it.
Nice.
Thanks, man. Good
Mine was the
catch.
same.
Okay.
Few more minutes for everybody, I think. Okay, I guess most of you are done. Let's get started. I see the quiz summary as 54% average score with high of 98% and low 20%. Average time is 8 minutes 47 seconds. Yeah, we could do better. Anyway, so let's get back to our discussion and problem. Let me do this problem first, show you, and I think someone asked me to show from the practice problem set. Can you please put it on the discussion so that I can follow up that on the next class? Okay, so uh, this problem. So remember, like we did a similar problem earlier to make a symbol table, right? But that time we used a relative address, which is basically the instruction numbers. Now we want to do it with a real address, since we kind of now have understood how the memory data is stored, how the information is laid down inside the memory, endianness, all these alignment issues and stuff like that. With all these respects, how these things are translated into a symbol table. So let's start doing it. This part, we need to treat code and data separately. Okay, so first of all, code and data, text part and the data section are stored in a different memory area, right? And as the problem statement said, we have given it a different power of start address. Like text goes into the 0004 that address, and data start from, let's say, 001 0000 that address. So let's try to make the symbols for the code part. So we have symbols and address. So data, okay, code starts from this specific address, means this instruction will be placed at this address, right? I'm not writing that extra zeros, but this address. And we all know each of these instructions are 4 byte. That means the next instruction will be starting at, like, with an offset 4. The very next instruction will start at, from the beginning at 8 plus 8. Uh, 12. 60, right? And we can always put and like instruction numbers associated with it. Like let's say this is number 1, this is number 2, this is number 3, this is number 4, and this is number 5. With these, and as we know, all the instructions are constant 4 byte. It is not a variable length instruction system. MIPS is a constant length instruction system. So we can actually formulate a quick data. Let's say this is my power up address. Power up address. So it will be instruction number n minus 1 multiplied by 4, isn't it? Either you can go with this way, or you can apply this general formula to calculate the address of the corresponding instruction. And we all know these labels are basically address of the immediately next instruction, right? So that means my main and L1 and L2 will have, so main will be starting from address address of the very first instruction, which is like 4000, and then for the L1 it will be the third one, So that means 4008, this guy. And the fifth one would be this one, right? So it will be like 4010. Question so far? Okay. Now,
I had a question.
yes.
So if there were any pseudo instructions in here, would that, I guess, affect the where the instructions are stored? That, I mean, pseudo instructions that like use multiple instructions.
Yes, that will. So in a problem wise, unless it is given specifically, I try to give it with mostly with the basic instructions, this type of problems. But yeah, if pseudo instruction is given and you can identify that, or if the problem itself is dealing with the pseudo instruction or has specific instruction about pseudo instruction, I might give you, okay, this specific instruction is composed by 3 basic instructions. In that way, case, you actually need to account for them. Does that make sense?
Yeah, okay.
Professor, can you repeat about L2? Why is 4010? I didn't get it. Because 16-bit add to the 4000?
Yeah, 16 in decimal, right?
Okay. Oh, 16 in decimal.
Yeah.
Okay.
These offsets are all in decimal. So 16 in decimal is in hex 10, right? Isn't it?
Yeah, got it.
Yeah. Sorry for the confusion on that part. All right, now your fun begins at the data section. Data section does not actually follows these uniformity rules. Like it is not that each data is following like 4 byte or 8 byte, something like that. You actually need to analyze them and apply also the alignment rule along with this. Okay, so let's start with the first one. STR. Okay, STR. Why don't I just write down all the label names first? So we need to make sure of the STR1 would be 1, var1, STR2, var2, STR3, var3. Okay, so those will be our entry, all the labels associated. Now, for the very first one is easy. STR will be starting from this start address, right? So let me just write down the lower half, 10000. Now, question becomes where this will start. For that, you need to count for that how many space this part is taking, how much space. So now we can count the ASCII Z, as we all know, it will store all these characters as 1 byte from that address, starting from that address. So it will be like 1 storage, 2 storage, 3 byte, 4 byte, 5 byte, and 1 more null character. Dot ASCII Z always terminate the string with a null character. So it will have like 6 byte of space. That means my next available level address is +6, which is 10006, right? Now question become, so I have stored 6 byte. Now we look for the var1 and ask ourselves, can it start from this address? This address. We see var1 at that level is trying to store a word. And we know word has to start from an address divisible by 4. And this address is not divisible by 4. So we need to move up to the next available address, which is divisible by 4. And that would be 0, 1, 0, 0, 0, 8, right? So this address starts from 1008. And a word will store how many bytes? It's always whatever the value, initial value doesn't matter. Don't count on that, because this guy will be stored as anyway 0, 0, 0, 2, no, okay, 1, 2, 3, 4, 0, 0, 0, 2, 4, F. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, like this. So don't just count this hex number of bits. It doesn't matter. It will always store a word, which is like 4 byte. That means my next available address is now is like this plus 4 byte, which is like 8 plus 4, 12, which is like A, B, C. Now we ask this str2, can this data be placed at this address? We see that, well, this is ASCII, like ASCII is nothing but a series of bytes of ASCII code. So we can start from there. So we place 100C there. Now we count how many bytes from there. It is 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. 5 byte, and remember, .ASCII does not include a include a null character, so it's still a 5 bytes. So that means my next available address is going to be like a 5 byte. C plus 5, 12 plus 5 is 17, which is 1011. 11.
I thought it was C plus 6.
Call from Mrs. Smartwatch.
So this one is a question.
I thought it was C plus 6, or I mean, world is 5 with the null 6.
But remember, .ASCII does not append.
Oh, no null. Okay.
Yep. So it's 1, 1. Now we want to see if this VAT2 can be placed at this address, which is not like half address. Half word needs to start from an even address, but it's an odd address. It is 17. So we need to start from the next address, 18, which is 1, 2. Now we start from the 1, 2, and we are storing how much? Like 2 bytes. So it will be now 1, 2 plus 2, which is like 1, 4, 0, 0, 1, 4. str3 ASCII Z, I can start from that. So no problem. 1, 0, 0, 1, 4. I can start from that, and that will store 3 bytes because ASCII Z is now contained like null character as well. So 1, 2, and null character 3. So my next address would be, available address would be plus 3, which is like 18, 23 basically, right? So it will be like plus 3, which is 17, 17. But 17, which is 23, is basically not divisible by 4. Oh, why? Because VAT3 is a byte. I can start from any address, no restriction. So we can start from 17 there. So that's how we basically make the symbol table for the data section. We need to be very careful about this address calculation and consider how many bytes are being stored at the specific directives, and if that address, that type of data can be placed, or we need to move the address to make the alignment criteria. Question? Okay, so I think we are over, actually due like 2-3 minutes. So let's end this class tonight here and see you on Monday.